Hey everyone. After talking about the linear probability model and what happens with OLS once we use it for binary outcome measures, now we're going to turn to introducing Logit and Probit as alternatives to model dichotomous dependent variables. Okay. And there are a couple of different ways of deriving both Logit and Probit as a model. Okay. One way I kind of hinted at in the discussion of the linear probability model, which is basically just focusing on this issue of modeling an underlying probability, where of course we shouldn't have out of bounds predictions, so we shouldn't have probabilities that are smaller than 0 or larger than 1, right? And so in order to do that, we have to specify a link function for these modeled success probabilities, right? So something that maps our linear predictor or our systematic component, which contains all the linear predictors and the coefficients, which, you know, that linear combination can range from -infinity to +infinity, and we want to map that to range just between 0 and 1 because we're modeling a probability rather than some continuous outcome. Okay. So the first kind of way to formulate and to derive the Logit and Probit is to kind of specify this link function to model success probabilities. There's an alternative kind of related way of thinking about Logit and Probit, which is to kind of think about, rather than kind of just directly modeling the success probability, we could also think about this problem as a latent variable problem. Okay. And the idea behind the latent variable approach to derive Logit and Probit is that, assume, for example, when we talk about this, or the prior example that we had in the linear probability video, where we talked about modeling the probability to vote for a Republican candidate in the presidential election, right? You could think of some underlying latent but unmeasured or unmeasurable variable that ultimately determines this choice, right? So for example, you could think of people's utility that they derive from one candidate versus another as such a latent variable, right? And so the idea here in this latent variable approach is that we basically use our systematic component to model this underlying but unobserved latent variable, such as utility in the voting example, and then relate this underlying latent variable basically through there's an observation mechanism where this latent variable ultimately results in voting for example, a Republican candidate versus voting for a Democratic candidate after we cross a certain threshold on that latent variable. So you could think of this as the utility being, larger than a certain threshold or something like that, right? I'll talk more about that in a couple of minutes. Probably I'll separate it in two videos, okay? The key point here is that those are both just different ways of understanding Logit and Probit and how we can derive the underlying model, but ultimately they both kind of alternative conceptualizations ultimately lead to the same models, right? And so depending on what is easier for you to kind of think about where Logit and Probit or the model specification is coming from, is fine. You can just think of these as alternative ways of conceptualizing how we come up with this specific model or these this pair of models essentially. Okay. So let me just start with the first alternative in this video, and then I'm going to move on to the latent variable approach in the second video. Okay. So the first way to kind of derive Logit and Probit starts with this issue that we described in the previous video when we talked about the linear probability model and the kind of related problem that a pure basic linear probability model can yield out of bounds predictions. So probabilities, predicted probabilities that are larger than 1 or smaller than 0, which obviously shouldn't be the case, okay? So we want to specify, instead of directly modeling this probability in a linear fashion, we want to specify a link function that basically maps the systematic component to the range from 0 to 1. Okay, so how do we do this? Okay, first we kind of want to specify this model and recall that we're basically thinking about an underlying Bernoulli process. Okay, so y, that's our outcome measure, that is 0 or 1. And we can think of this as the outcome of a Bernoulli process with some success probability pi n. So Bernoulli, keep in mind, that's just the simple coin flip to model a dichotomous outcome. Note here, though, that there are, when we talked about Bernoulli in the beginning, when we talked about basic probability theory, we often talked about Bernoulli trials with constant success probabilities. This is not the case here. Right now we have success probabilities that basically differ between individuals, right? Not everyone has the same probability to vote for a certain candidate, or not every conflict has the same probability to result in civil war, right? Ultimately, we want to find predictors that help us determine whether some probability is higher and some probability is lower, right? So this underlying success probability pi has a subscript n because they're different probabilities for each observation, okay? But of course, it's not just that we just, have a different probability pi n that we estimate for each individual observation, because ultimately such a model, if that was completely, if all the pi's, all these success probabilities were completely unconstrained, so to speak, then this model wouldn't be identified, right? Because we would have to estimate one success probability for each individual observation, right? So in order, we need to make some additional assumptions of how to model this success probability pi n, and ultimately we want to relate it back to the predictors that are included in our model, okay? And this is where ultimately our systematic component comes in, and this is should look familiar to how we discussed this in the linear probability case. We have our expectation of our dichotomous outcome measure, which is equal to the probability of observing a 1, which we can also write as pi n in this case. And again, n, this has a subscript n because each individual probability is the probabilities differ between individual observations, but as I mentioned, they're not just completely unconstrained and just, we just estimate a random or some probability for each observation, but rather we're modeling this probability with the systematic component, the linear combination of all our predictors times our coefficients, so that's beta prime xn, just the same way as we have in the linear probability model. But now on top of that, we have this g function. This is the link function that ultimately takes this systematic component and maps the linear combination of those predictors and coefficients essentially to the range from 0 to 1 to model the probability. Okay. So this is the basic setup, right? This is kind of just an extension of the way we kind of thought about this problem in the linear probability case. The only addition, essentially, is that we have this link function g. Okay, and so obviously the question we have to answer is then which link function g should we choose? Okay. And there are different possible link functions that we can choose from, and two that are used as standard link functions for problems such as this are either the cumulative standard logistic function, which results in the Logit model, and on the one hand the cumulative standard normal, which we've seen before, which ultimately results in the Probit model. Okay. Both, and I'm going to kind of show you a comparison and how exactly they look like in a second. But ultimately, you can think of the kind of the difference between Logit and Probit is just the difference in this link function, right? Both link functions do essentially the same thing, right? They take our systematic component, our predictors and our coefficients, and map that to range into the probability space between 0 and 1. That's all they do. And they do that in slightly different ways, but ultimately the underlying, the resulting quantities of interest based on the Logit model and based on the Probit model are essentially the same. Okay, so both models always give you the same results. The coefficient just look slightly different because we use a different link function. Okay, so as I mentioned, in practice, both model specifications, Logit and Probit, lead to the same substantive results. We can compute the same quantities of interest, the same underlying probabilities, and so on, based on the Logit model as well as the Probit model. And the reason for that is that the standard normal and logistic distribution actually have a very similar shape. And we can actually, if we have the model results from one and compare it to the other, we can actually transform the coefficients from a Logit to kind of approximate the results from a Probit model. Okay. So to start, okay, I'm just going to go through the math very briefly to just show you how the link function for the Logit model and how the link function with the Probit model looks like. And I'm going to just show you briefly the basically deriving the log likelihood function. If you remember back a couple of weeks ago, we kind of derived OLS using maximum likelihood. And so we could go through the same process here. But ultimately what we're going to do is we're going to directly move on to using kind of prepackaged functions, both kind of the classical base R functions and stand functions, to then estimate the model, these models, right? But in theory, once you see the once you see the log likelihood specification for both the Logit and the Probit model, in theory we could go through the same practice of setting up this likelihood function in R and then maximizing that likelihood function in order to find our point estimates. Okay, so the structure is ultimately the same. It all kind of fits in this maximum likelihood framework that we've talked about in past weeks, and ultimately, combining that then with prior information, and then rather than maximizing but sampling from the posterior distribution, results in our Bayesian Logit and Bayesian Probit model. Okay, but I'm skipping too far ahead. Let's just go through the math real quick, and let's begin with the Logit model. Okay, so again, just keep in mind as you go through this and as you look at the math, keep in mind that all we want to do is we want to find a link function that maps our systematic component, our predictors, to basically the range from 0 to 1 to model the underlying probability of observing a 1 rather than a 0. Okay. One common function to do this is the Logit or the inverse Logit function, which looks as follows. It's e to the power of beta prime xn divided by 1 plus e to the power of beta prime xn. And we can further simplify this. We can divide by e to the power of beta prime xn in the numerator and the denominator to specify this like this: 1 divided by 1 plus e to the power of minus beta prime xn. Okay, this is just one link function out of basically a universe of potential link functions we could use, but it's one function that has this property that we want. The property is that we can plug in any type of number here for beta prime xn from minus infinity to plus infinity. If we plug this into this function, this will always be mapped into the range from 0 to 1, right? So if this beta prime xn is very, very small, then this overall term will approach 0. And if this beta prime xn is very, very large, then this overall function approaches 1. Okay, just quickly, so to the power of negative, that's 1 divided by e to the power of beta prime xn. If this is very, very large, then this overall term here is basically almost 0. And then this is basically almost just equal to 1 divided by 1. So this is the probability approaching 1, essentially. Okay. Okay, so this is just one function that basically fulfills the task that we wanted to fulfill, which is mapping our systematic component onto the range from 0 to 1. Okay, we can then use this link function to specify our log likelihood function first for each individual observation. The log likelihood contribution for each individual observation n, we can specify for dichotomous trials as follows. We have yn times log of pi n plus 1 minus yn times the log of 1 minus pi n. Pi n is the success probability. We're going to plug in our link function in there in a second. And of course, this sum, one of these elements of the sum drops out depending on whether yn is equal to 1 or whether yn is equal to 0. Okay, so it's a straightforward way of specifying this log likelihood contribution for this dichotomous outcome. Okay, of course, if we want to compute the overall log likelihood function, we have to sum up all individual contributions by assuming independent realizations. So this is this basic IID assumption that we talked about, and then we have our sum of from 1 equals 1 through n, from n equals 1 through n of all these individual log likelihood contributions. And then, as I mentioned, we plug in our link function, our parameterization of pi n, which is just 1 divided by 1 plus e to the power of minus beta prime xn. And that is our log likelihood function for the Logit model. Okay, and as I mentioned, we could now kind of program this up. We could maximize this with our observed yn, our observed axis, and then maximize for beta, for our beta vector to get our maximum likelihood estimates for this Logit model. Okay. We could do the same thing with a different link function. Instead of this logistic link function, we could use a standard normal distribution or a cumulative standard normal distribution to map our systematic component to the range from 0 to 1. If we choose the normal distribution or the standard normal distribution with variance 1 for our link function, our probability of yn compared to the specification up here looks slightly different. This is just the cumulative normal distribution, taking the integral of the normal density up to the point beta prime xn. And we can usually, since this doesn't have a closed form solution, we usually just write this as phi beta prime xn. And we can basically go through the same process. We can, based on this kind of parameterization of pi n, we can specify the log likelihood contribution for each observation, which is the same as before. The only difference now is that our pi n looks slightly different. Rather than using the logistic link function, we now have this phi beta prime xn in there. Okay, and again, we sum all of those up, and we could now basically program this in R, and then use the observed y, the observed axis, and then maximize this likelihood function to find our point estimates that are basically most likely to have generated the data that we observe. Okay, and that would give us our Probit model estimates. Okay, so why do we use Probit versus Logit? Ultimately, as I mentioned, both models ultimately give us the same substantive results. The same, if we compute our quantities of interest, the underlying probabilities, we get the same results between the Logit and the Probit. Right? You will not, it will be very hard to find a substantive example where using one model versus another model provides you with a different answer. Right? There are some reasons why some, in some cases, Logit is preferred versus Probit, sometimes historically due to computational constraints, where sometimes the Probit model is computationally a little bit more difficult or a little bit less tractable. But other than that, you can essentially go back and forth between those two, right? There are also other types of link functions theoretically that we could use in order to map our systematic component to this range from 0 to 1. But Logit and Probit are the key or standard alternatives, okay, that you'll see in the literature. Okay. In terms of how they are different, one thing that I did here quite just quickly using base R functions is to plot both the logistic and normal density as well as the cumulative normal distribution and the cumulative logistic distribution, just to show you that for the cumulative distribution, which is here on the right hand side, we have basically both are link functions that fulfill the requirement that we had, which is we want to map something that ranges from -infinity to +infinity into the range from 0 to 1, right? So we can plug in different values here, and this is mapped between 0 and 1. The function is bound between 0 and 1, or the function output is bound between 0 and 1, okay? But because the logistic function has slightly wider tails, essentially, okay, it's a slightly wider distribution than a standard normal distribution, we see here that this cumulative distribution has a slightly less steep a slightly less steep slope, okay? So the shape is slightly different in terms of the underlying link function, but the resulting effect that we're mapping a systematic component to range from 0 to 1 is the same, right? The only thing that is different is that the coefficients, because of the different link functions, the coefficients will look slightly different, okay? But based on the differences in the variance and basically in the slope of this link function, there's a kind of a scaling between logit coefficient or systematic difference between logit coefficients and probit coefficients, right? So as you can see in this graphic, the logistic distribution has wider tails. So it's basically the standard normal, of course, has a variance of 1. The logistic distribution has a variance of pi squared divided by 3. And so because of this difference in the densities and the resulting difference in the slope of this link function, we can basically see, and I'm going to show this in an example in some of the later videos, that the Logit and Probit coefficients always differ by a factor of about 1.8, and that is just pi divided by square root of 3. We're not going to go through the math of showing why that is the case. The way you can think about this and the way you can keep this in mind is that these are just different alternative link functions that fulfill the same goal, right? The goal, again, is to map our systematic component that ranges from -infinity to +infinity up to the underlying probabilities that we want to model, which should range from 0 to 1. This link function has a slightly different shape for the Logit and the Probit. And because the shape is slightly different, that means that the underlying coefficients that we're going to estimate that determine the underlying probabilities that we want to model also look kind of different. They look slightly different, right? But because the difference in the link functions can be characterized by this kind of systematically lower slope for the Logit, we know, or we can show that the Logit coefficients and the Probit coefficients always differ by a certain factor, and that factor is 1.81. Okay, that's just the kind of the extent to which we will kind of go into the weeds and the depth of that distinction. Okay. The key point to keep in mind is that whether or not you use a Logit or a Probit, both models ultimately produce the same quantities of interest, right? So these are just difference in the coefficients, which is again the systematic component beta prime, the betas that are then combined with our predictors. But the underlying probabilities that we're ultimately modeling, right? The success probability, the probability of observing a 1 rather than a 0. Those quantities of interest, they are the same, right? We're still estimating the same probabilities. We're just quantifying them differently because of the different link function. Okay, so the substantive results regarding the quantities of interest that we're actually, substantively interested in, those are all the same. Okay. All right, I'm going to take a break here, and then in the next video we're going to talk about Logit and Probit, or deriving Logit and Probit using this latent variable approach. Okay.